G'day. We're looking at integrating, we're using the substitution rule today. So we've looked at integration in terms of inverse substitution. We've also looked at using a natural log. What we're going to be looking at today is those types of integrals that we can't integrate in a normal method. So when it comes to integrating the substitution method, it's basically integrating the reverse of the chain rule. And we have certain steps that we take to be able to calculate this integral, and we look at using something that we call substitution, where we substitute one variable out for another, so that way instead of having in terms of x, we have it in terms of, the most common one will be u. So when we look at integrating and using the substitution method, we usually have about 5 steps that we go through. So let's have a talk of these steps here. The first and probably the most important one is picking the u expression. So when we're looking at picking the u expression, we're looking to look for expressions that are either the longest part, or examples such as if we have 1 over x to the power of n, or root, something over it with a root, or 1 over the square root, or we could have e to a power, or we could just have something like 1 over, we've got that one up here, or just x to the power of something. So if we're looking for something in terms of a u expression, these here are the first things that we look for. If we have two certain functions that have the same, so for instance if I had sine 2x over cos 2x, we generally try and go for the one that's down the bottom. In that case, we would get a logarithm to help us calculate and solve. So that's probably the most important thing when it comes to calculating your u, or finding your u in this substitution method. Once you've found that, we then find what du dx is of that u. Once we've worked that part out, our ideal scenario is to be able to replace what we found as u and our derivative of u back into the original equation. So that way everything is in terms of u instead of x. If that works, fantastic. If it doesn't work, then we're going to have to start manipulating those u's and du dx's around to fit into the expression. Once that's done, we integrate as normal using u. And then when we get to the end, we replace that u back with the expression that we started off with. So let's get into some examples, just so that we can see how these questions are done. I've got some up on the board. We're going to be looking at 5 different methods here, and the last one is going to be dealing with definite integrals, which is a little bit different. So let's get into this method. First one here. We've got 3x squared, x cubed plus 5 to the power of 7. So if we look at this first question here, we can say that u, let's get a better texter, here it is, u is equal to, inside the brackets, x cubed plus 5. We don't have to worry about the 7, we're only dealing what's inside those brackets. So therefore, du dx is equal to 3x squared. Now another way you can write this here is you could write it such as du is equal to 3x squared dx. I like it this way because that way if I'm manipulating, I know what I'm fitting in. I'm replacing the 3x squared and the dx, and I'm also replacing the x cubed plus 5. So this here is an ideal situation. U, x cubed plus 5, I can just plug in with u. And I can replace dx and 3x squared with du. So if we look at this question here, we now have u to the power of 7 du, where we replace dx and 3x with du, and we replace x plus 5 with u. And now we're ready to start integrating. Now in terms of u instead. So this then becomes u to the power of 8 over 8 plus c. So we've integrated this correctly now. All we need to do here is we've found u, we've plugged it back in, we've integrated. We now just replace u with the expression we started off with. So therefore, we get 1 over 8 x to the cubed plus 5 to the power of 8 plus c. And this here is the integral of this first question up here. Alright, let's have a look at the second one. So the second question is a little bit different. Let's identify again which one our u is. So u, again, 1 minus x to the power of 4. We now want to differentiate this. So du is equal to negative 4x to the 3 dx. Alrighty, I can replace 1 minus x to the power of 4 with u. But I have nothing that I can replace in terms of x cubed. But what I can do is I can manipulate the negative 4x cubed to be able to fit into this. And one way I do here is I'm just going to divide everything by negative 4. If I do that, I get negative 1/4 du is now equal to x cubed dx. Ha! Now I can replace the x cubed dx with now negative 1/4, and I can replace the 1 minus x to the power of 4 with u. So let's do it. We get negative 1/4. I might plug over here 1 over u and du. Now, doing it like this here, and I better put this here as a square root because it was a square root. Let's integrate. We can pull our negative out. So we get negative 1/4 u to the power of negative half du. And now I'm ready to integrate. So integrating gives me negative 1/4 times u to the power of a half over a half plus c. We know that we can simplify this up to be negative 1/4 times 2 over 1, because remember this here is going to become the reciprocal of the square root of u plus c. I'm just changing this back into the square root, which then gives us the answer of negative half square root of u plus c. So this here is not the answer yet. This is in terms of u. We now have to do that last step, which is replace our u with what we have as our first expression. So therefore, we get negative half square root 1 minus x to the power of 4 plus c. And that here is our integral of x cubed over top of 1 minus x to the power of 4. So we're doing those steps here. We find the u expression. We find the du of that expression. Try and plug it back in. It doesn't work, let's manipulate something. Once we finish that manipulation, we then integrate in terms of u, replace our u value back in for where u is, and there is our integral. Alright, let's continue on. Let's have a look at the next example. So our next example is a little bit different again. We know that our u expression